Good morning and good afternoon, everyone. Let's welcome to the C2SR Distinguished Webinar Series in Artificial Intelligence and Cybersecurity. So, on behavior of the Center for Cybersecurity Research at the University of North Dakota, thank you all for joining us today. And it is my pleasure to introduce our distinguished speaker, Dr. Subhash Lakshminarayana, associate professor in the School of Engineering at the University of Warwick in the United Kingdom. And Dr. Subhash research focuses on the cybersecurity and the resilience of power grids, particularly the application of machine learning, optimization, and the control techniques to power grid security. And his work has received several recognitions that includes the Best Conference Paper Award at the 2024 IEEE Smart Grid Communication Conference. He was also recognized among the top 5 authors published in the IEEE Transactions on Smart Grid in 2022. So in addition to his research contributions, Dr. Subhash serves as an associate editor for the IEEE Transactions on Smart Grid and as chair of the IEEE Smart Grid Communications Technical Working Group. So his research has been supported by several funding agencies like EPSRC, Innovate UK, and Horizon Europe. And today, Dr. Subhash will present a talk titled Moving Target Defense for Defending Against the Adversarial Attacks in Power Grids. So he will discuss how periodic or event-triggered changes to the power grid systems can help invalidate the attacker's knowledge, disrupt the stealthy attacks, and strengthen the security of both physical infrastructure and the machine learning applications in power grids. So we are pleased to have him with us today, and please join me to welcome Dr. Subhash. So now, Dr. Subhash, the floor is yours.
Yeah, thank you. Thank you very much, Gillian, for the introduction, and thanks to the whole team for organizing this and inviting me to provide the webinar. So I'll try to share my screen. We should go. Yeah, can everyone see this? Yeah.
Yes.
Okay, so we can start. So today I'm going to talk about some work we've been doing on adapting moving target defense to power grid scenarios, particularly the adversarial attack against machine learning algorithms, that are kind of the Achilles heel of machine learning in a way. I'd like to thank a couple of my students, former postdoc, Dr. Yeshang Chen and Dr. Hamid Reza Jahangir, who've helped me in a lot of these works. So just a quick introduction. I'm based at University of Warwick. So Warwick is in Midlands, slightly in the center. We are about an hour and a half from London, hour and a half from Wimbledon, if some of you are watching tennis these days. So yeah, Warwick is a part of Russell Group University, which is sort of the Ivy League kind of equivalent in the UK. And yeah, it's rated the 8th best university in the UK at the moment. In terms of my research group itself, so I work on the topic of cyber resilience of power systems, mainly bringing together things around topics around cybersecurity, cyber physical system modeling and control, and application of machine learning. And in addition to work on power grid, I've also worked on electrified transportation, particularly cybersecurity of railways, cybersecurity of electric vehicles, along with the charging stations. And I also work on a little bit on wireless communications in my past research. Right, and as Jilun mentioned, so we work funded by several UK and European research organizations, and we also work with several UK-based industrial collaborators. We have the National Grid and National Electricity System Operator, which are the main transmission network operators in the UK. Also, Northern Power Grid, which is a distribution network operator, Schneider Electric, some EV charging companies, and so on. So, moving to the topic of today's work. So I'll start with a very quick introduction to AI for power grid operations. So I think I don't need to go into much detail. So I think everyone here is convinced and has seen a lot of works, using AI for enabling different functionalities in the power grid. So AI can be used for a variety of applications like providing situational awareness, forecasting, DER coordination, predictive maintenance, and also, yeah, mainly cyber physical attacks as well. So how can we detect these attacks, and even use things like LLMs for operator grid support and things like this. So when it comes to AI and cybersecurity, so AI is a double-edged sword. Okay, so on the one hand, AI can be used to do a lot of cyber attack detection, but at the same time, AI itself can be vulnerable to adversarial attacks. Yeah, so I'll shortly present, if you can corrupt the inputs to the AI system, it can end up giving like completely different inference decisions, which can then throw off the whole help that AI is providing us, because then you can have like incorrect operational decisions affecting your system, right? So it's a two-way arrow. So on the one hand, it can be helpful, but on the other hand, AI itself needs cybersecurity measures embedded into it in order to function in a reliable and resilient manner. So AI for cybersecurity, I think, as I mentioned, I think a lot of works are there, at least in the past 7, 8 years. So there have been a number of works that are looking at monitoring AI, the power grid signals, network traffic, physical information, and then use a lot of tools that are developed in the AI literature in order to, detect these attacks and so on. So I won't go much into this because this is sort of a well-studied topic. I've also listed a couple of works from our groups, but I mean, this is by no way exhaustive. There are many, many works out there, right? So yeah, I mean, I think that I'll focus on the other direction. Basically, how can you provide cybersecurity for AI? And the problem here is illustrated in this picture here. So the idea of adversarial attacks comes from the machine learning literature. So this is if you have an image classification machine learning model that is able to classify different objects, right? So you provide the image here, which we all can see is a panda. However, if you add some clever adversarial perturbation, this turns out to be an image that I'm showing on the right-hand side. So for a human eye, we can clearly say that this is still the image of a panda. But for an AI system that has been trained on data sets, it will completely make an incorrect inference. It concludes that there's an image of a gibbon, and gibbon is an animal that looks more like a monkey, right? So whereas for a human eye, it's really obvious that it's still a panda. The AI gets completely confused. So you can draw analogies from here to machine learning in power grids. So if in the power grid scenario, the inputs are corrupted in an intelligent manner, you will end up making incorrect decisions, and this can be very consequential for cybersecurity as well as when you're using AI for providing grid support system, right? So the obvious question is, how can we make our detectors robust to these types of attacks, especially in the context of power grid? And to address that, we've been working on adapting what we call as moving target defense. So the moving target defense is this idea of introducing controlled changes across multiple dimensions to the grid, right? So think of playing a dart game. So if somebody is moving the dartboard around, obviously as a dartboard striker, you'll find it really hard to aim your attacks, right? And this is exactly the same concept. So if your system is static, the attacker can learn its operational details and they can target the right system and design stealthy attacks. However, if you're moving the system periodically, you will end up confusing the attacker. So in a way, you're breaking the asymmetry between the attacker and the defender, right? So you're taking the game to the attacker in some sense. And the idea basically comes from network security. So things like network address space randomization. So for example, if you're working on a static IP, then the attacker can know, which IP addresses are the PLCs are working on. However, if you randomize the IP address, then the attacker will also get confused, right? So similarly, in a code, you can also randomize the instruction set so that the attacker can then attacker won't be able to know exactly what instructions are there within the PLC logic or something like this, right? So what we'd like to do is take this idea and then adapt it to Power Grid scenario, especially the adversarial attack that I was talking about. Okay. So this basically translates to changing some settings within the Power Grid, and I'll maybe shortly tell you what things can be changed in the Power Grid. But the fundamental design questions for MTD are these three. So the first one is, what do you want to change? The second one is, how frequently do you want to change? So when do you want to change? Do you want to change it every 1 hour or every day, once a day or something? So what are the trade-offs that are involved there? And the final question is, how much do you want to change, right? Because if you change a lot, then you're also disturbing the regular operation of the system. So these are the three fundamental research questions that you need to answer in any moving target defense design. And yeah, so we've written a survey paper recently on this topic in IEEE Open Access Journal on Power and Energy in collaboration with some of the people. So this Professor Harris Constantinou from KAUST and also Anurag Srivastava from University of sorry, I forgot, West Virginia. Yeah. So we've done extensive work and also done some survey papers around this. So basically, the first question is, what can you change? So there are a number of things you can change within the Power Grid network. You can change the physics of the system. Basically, when you talk about cyber physical attacks, where you have like false data injection attack that is trying to manipulate some physical measurements, you can change the physics of the system in order to invalidate the attacker's knowledge. Okay, so you can change the line reactances, you can change the measurements that are being used for state estimation, and so on. You can also change things at the network layer itself. So, because we're working with cyber physical systems, we have a physical layer and then we have a cyber layer, right? So I can also change things at the network layer, like you can randomize the routing of the packets, or you can randomize the IP address and so on. And finally, you can also change some things in the machine learning implementation, which I'll highlight later in the talk. Right? And just to give you a quick idea, so when you're talking about things like network-based MTD, what you're basically saying is that you're going to change the route. I mean, there's one way to implement it, of course, there are different ways. But what you could do is you can change the route that the packets are taking to reach their destination. Okay, so if one of the line is congested, you can switch to another line, or if the attacker is launching some denial of service attacks, they are flooding packets along one route, you can change the route of the you can change the route and then invalidate the attacker's knowledge in that manner, right? So you need like things like software-defined networks to dynamically change the routing, but if you have those functionalities, you can definitely do this kind of dynamic routing, right? And in physics-based MTD, so there are different ways again in which you can do it. You can change the line reactances using some devices that we call as the DFAX devices, or you can change the measurements that are being carried out. You can change the topology of the system and so on, right? So it turns out that the physics-based MTD is very well researched. I mean, this is where a lot of works have come up, and then we've also done within our group some of the fundamental work in this area of how much to change and things like that. And also you can think of MTD as, classifying MTD as in which stage of the attack will the MTD work. Okay, so you can say that MTD can be used for attack prevention. So if the attacker is aware that the things have changed, what they may do is they may withhold the attack, right? So if you're an attacker, you're doing some reconnaissance, you're trying to understand the environment, and then after some time, you realize that things have changed in the system, then you may withhold the attack. Okay, so if you're doing this in a fast enough manner, you may make the attacker like completely withhold the attack. So in that case, it can be used for attack prevention. On the other hand, if the attacker is unaware of these changes that you're making, they'll anyway launch the attack. But because the system has changed from what they have learned, during the reconnaissance phase, their attack is going to be detected. Okay, so this is what we call as the attack prevention. You can call it the ex ante, and the attack detection is more like the ex post. Or you can also use it for attack mitigation. So as I was mentioning, when the attack is launched, if one of the lines has been congested because of a DOS attack, denial of service attack, you can change the routing to another point in the grid, another path within the network, in which case you're basically mitigating, you're recovering the system from the attack. Okay, so these are different ways in which moving target defense can be used. And finally, there's also this fundamental trade-off. As I mentioned, if you're moving things in the system, you're also changing the operation of the system itself. Okay, you think of it as introducing a very large perturbation. So the question of what is large, I'll maybe go over it shortly. So if you can introduce a large perturbation, you're very effectively invalidating the attacker's knowledge, but at the same time, you're causing the grid to operate significantly far away from the optimal state. Because remember, the line reactance, topology, things like this are optimized to minimize the generation cost or things like that, right? So if you're changing things in the system, you're also disturbing the operation of the system. So there's always going to be this sort of trade-off. Yeah. So how effectively I can invalidate the attacker versus how much disruption I cause to system operations, right? So that's kind of my lengthy introduction to the MTD topic. And now, so let me go into more details of the actual system that I'll work with. So basically, we will look at what we call as the false data injection attacks in the system, right? And these are again very popular attacks. People have been researching on this since almost 2010, which is like 15, 16 years ago, right? Um, and you have physics-based attack detectors, right? Like bad data detector and so on, that are vulnerable to some sort of sophisticated attack. If the attacker can learn sufficient details of the system, then they can bypass these bad data detectors. And then people then introduced these machine learning based detectors. What the narrative at that time was that these physics based detectors, if the attacker can learn the physics of the system, these attacks can be detected. So let's use more sophisticated detector, which is the machine learning based detector, right? That can catch all these bad data detector bypassing attack, right? However, what's been realized now is even this machine learning based detectors are vulnerable to this adversarial attack. So we'll design moving target defense to cover this whole kind of scenario. Okay, physics based strengthening physics based attack detection as well as strengthening machine learning based attack detection. So I'll sort of first start with the physics based detector and how to strengthen that using moving target defense, and then later move on to the machine learning part of things. So yeah, I mean, so false data injection attack, very quick introduction to somebody that doesn't know it here. So basically you are talking about a power grid physical plant that is being monitored at the control center by deploying sensors, and then there's communication links, which are using things like Modbus or 61850 protocols and so on. And there's a underlying communication network, which is basically transmitting all the data, right? And when you're talking about false data injection attack, what you're saying is basically there's an attacker that can that can hack into this system through like spoofing, ARP spoofing, and things like that, and they can manipulate the packets and the payloads that are going in there. So basically, in terms of the mathematical modeling, if we say Z is the set of measurements, then you have an attack vector A, which is basically the additional false data injection attack that the attacker is injecting on the original measurements of the system. So think of Z as things like power flow, line injection, and A is basically the injection that the attacker is adding onto the system, right? And obviously, if this attack vector is arbitrary, all you can do some very simple checks. You can check, okay, are the measurements that I'm recording following the physical loss on the system, right? And that's what basically the power grid bad data detector does. It effectively verifies that that the measurements you're receiving are following the physical loss in the system, right? So if it's an arbitrary attack, these attacks will be caught by the bad data detector. However, if the attacker knows the measurement matrix H, which is basically something that depends on the topology of the system, which is the connectivity and the line reactance of the system, right? So if the attacker has the ability to learn learn the operational details, what you can show is that these kind of attacks can bypass the bad data detector. Okay, so this is a very famous result. I mean, this is more than 15 years old. It says that if the attack lies within the column space of the measurement matrix, right? Again, this is something that depends on the physical parameters like the line connectivity and things like this. So if the attack lies in the column space, then these types of attacks will be undetectable by the bad data detector. So the first question is, how can we harden this, right? So how can we harden the physics-based detector? And then I'll go on to the machine learning-based detectors. So the way to do it, as I said, is you need to understand what is it that the attacker needs to learn, which in this case turns out to be like the measurement matrix, which, as I said, depends on the topology and the line reactance and so on. So why not change the line reactances, right? So why not perturb the line reactances or even the topology of the system? So how can you do that? You can perturb the branch reactances by what we call as FACS devices, which are some sort of power electronic devices that can dynamically change the line reactance. So if you can do that, you're invalidating the knowledge of the attacker's knowledge of the measurement matrix, right? And then the attacks are going to become detectable. Yeah, so this is just a quick introduction to FACS. So FACS are these power electronic devices, which are kind of low-cost devices that you can attach to transmission lines to change their line reactances. So they are in there, to control the power flow. So there are times when the grid can get very congested, in which case you need to reroute the power through some different lines, right? So these need not be deployed, specifically for cybersecurity, but the point here is that these are pre-existing devices that are there in the system to, like route the power flow and so on, right? So why not make use of them to also provide cybersecurity, right? Specifically to thwart these kind of cyber physical attacks that I talked about, right? So the question is, how do we change, right? So then this question becomes, how do we change? Which line should I change? How frequently should I change? And things like that. So for this, you need to do some mathematics. You need to go into some mathematics. So as I said, if if the attack lies in the column space of the measurement matrix, it can be detected. So you can do something very arbitrary, in which case you change the line reactance of every transmission line by a similar amount. Okay. So if you're doing something like that, you're basically transforming this measurement matrix H to something which is H prime, which is just 1 plus eta times H, where eta is a factor in which you change the line reactance. But these type of perturbations are not useful, okay, because as you can look here, by just doing this linear combination, you can see that the column space hasn't changed at all, right? So it's just a linear scaling, whereas the actual column space has not really changed. So these kind of perturbations are quite useless, okay? So what this means is that you must cleverly design these perturbations. You can't just arbitrarily change something and hope that, it works well. On the other hand, the best thing you can do is basically make the measurement matrix, the column space of the measurement matrix, orthogonal to the column space of the original matrix. Okay, because attacker designs their attack with the outdated knowledge, so that means that their attack is going to lie within this column space. But the measurement matrix has now changed, and the column space has become completely orthogonal. If you work out a little bit of the mathematics, you can see that this is the best thing that you can do, is to be able to detect all the attacks. But the question is, I mean, can you always achieve this? Okay, so can you always achieve this orthogonality condition? Because this may sometimes mean that you need to change the line reactance by a significant amount, or you need to change the line reactance of all the lines and so on, right? So in reality, what you would like to do is, I mean, do something in the middle, right? So the question is, what comes in the middle? I mean, you basically would like to orient the column space, at a certain angle. Again, you can work out some higher dimensional linear algebra stuff. So there's something called as principal angle between different subspaces and things like that. So you can use these metrics as a way to design your moving target defense perturbations. Okay, so As I said, arbitrary changes are not going to be effective, but you can say that I would like to design my perturbations to increase this smallest principal angle between the column space matrices and so on, right? Yeah, so this is something that we did in this work, which was published in Transaction Power Systems. So it was done a while ago, but it's still like relevant, especially for the adversarial attack that I'll show, right? And also, as I was saying, there is a trade-off, and the trade-off here is the increase in operational cost. Because if you do not have cybersecurity concern, you would optimize your entire system to minimize the operational cost. Now you're changing the line reactance to certain amount, so you're going to change the operational state of the system. That then leads to increase in the operational cost, which is the optimal power flow cost, right? So we characterize this trade-off, which we call as the cost-benefit trade-off for moving target defense. And this is one of the main results. On the x-axis, I have the effectiveness of the moving target defense. On the y-axis is the increase in the cost, right? So you can see that more effective MTD perturbations also result in higher cost, right? Which is something that you can that you can sort of anticipate. So if you're a grid operator, then you can say, okay, what is my risk appetite? How much additional investment am I planning to make, right? How much can I increase my operational cost? And then you're going to choose a perturbation based on those trade-offs. Okay, so what we have done here is provided these kind of trade-offs curves based on the mathematical analysis that we did. So moving forward, so the question is, how can we take this to the machine learning literature that I was talking about? So how can we adapt moving target difference to machine learning? And as I said, the problem there is that AI can completely misinterpret if you add some additional perturbation to the system, right? And it's more of a problem in a safety critical system like autonomous driving, right? So if you are misreading a stop sign, that's going to be really bad. And we all know that power grid is also a safety critical system, and we cannot afford to make mistakes. Uh, so if you look at the literature around adversarial examples, adversarial literature, machine learning, so the adversarial attack can happen both during the training phase as well as the inference phase. So during the training phase, what it means is that you corrupt the training data such that the machine learning model that's developed is basically incorrect, right? And at the inference stage, what this means is that you have a trained model that is working well, but at the deployment stage, when you're passing data in real time, you add some clever perturbations to the data in real time. Okay, and then that will lead to misclassification and things like that, right? So this, for example, is an inference attack. So you're basically adding some sort of a sticker to the stop symbol for it to then be interpreted as something incorrect. Right? So I'm mostly going to focus on the inference time attacks. Maybe data poisoning attack is something that could be also done moving forward. Uh, so continuing the story from the false data injection attack that I talked about. So basically, as I was saying, so if you have an attack, if you have a measurement vector Z, and you're adding you're adding a perturbation A to bypass the bad data detector attack, right? So you have an attack of the form A equal to HC. And then what you're saying is that this type of attack, Z plus A, can be detected by the machine learning based detector, because this attack detector, these measurements have not been designed to bypass the machine learning based detector. They've been designed to bypass the bad data detector, but the machine learning detector can catch them. So why not add some additional perturbation in order to make sure that this overall attack is able to bypass both the physics-based detector as well as the adversarial detector. Okay, and this is one way in which adversarial attacks in Power Grid are actually different from image processing, because if you just add a delta to bypass the machine learning based detectors, this overall attack could then maybe be caught by the bad data detector itself. Okay, whereas what you will need to do is design an overall attack to bypass both the bad data detector as well as the machine learning based detector. So I won't go into all the details of how to design this overall attack because there's a bit of mathematics involved there. So it's based on what we call as the Kalini and Wagner algorithm, which is one of the famous algorithms in machine learning literature. So what we can do is adapt the Kalini and Wagner methodology in order to make sure that this overall attack still lies in the column space of the measurement matrix. Okay. So that is something that I'll probably skip because what I'd like to focus on is how can we design moving target defense. So the fundamental issue in any machine learning detector is that basically, let's say you're designing a classifier that is trying to differentiate between these green points and the red points, and then you have a decision boundary, right? So the fundamental problem is that this decision boundaries are static. Okay, so if the decision boundary is static, what the attacker can do is they can learn the decision boundary and they can take points that are very close to decision boundary. So X is a point that's very close to decision boundary, and they can add some clever perturbation to basically, take this adversarial input to go over the across the decision boundary, right? And that's the way in which these adversarial perturbations actually work because you're basically flipping the or moving the adversarial perturbation to another point in the system. Uh, so what we can do now is, in the spirit of moving target defense, we can try to randomize the decision boundary. And how can you do it? You can do it by what we call as deploying a pool of machine learning models. Okay, so instead of deploying one single machine learning model, because the attacker will have the ability to learn this over a period of time, right? By querying and so on. Why not design a pool of machine learning models? Okay, which will then mean that the attacker cannot really know the exact machine learning model that you're using, and they'll get confused. So this is another result that we recently published in IEEE IoT journal. So what are the design questions? So the design question now becomes, how can we minimize the adversarial transferability across the pool? Okay, what that means is that if there is an attack that bypasses the first DNN, the first machine learning based detector, that attack should not also bypass the second one. Okay, because if there's an attack that bypasses all of them simultaneously, then the attacker wins, right? So you need to cleverly design your machine learning in order to ensure that an attack that bypasses one of the machine learning model does not bypass the second machine learning model. Okay. And also the second thing you need to do is maintain accuracy over the original data. So this is sort of the trade-off that I was talking about, right? So how can we do it? So the idea is to then design this pool of machine learning models, right? The way we do it is we take a base model and then we add some perturbations to the weight of the model, and then we retrain the model. Okay, we retrain the machine learning model because any machine learning training is inherently stochastic, right? Because it's an empirical averaging, right? So retraining basically does help, especially if you diversify the data with which you retrain these models. This does help in reducing the transferability across these models. Okay, but there is a catch. I mean, I'll also explain how you can, further strengthen it. And yeah, I mean, there's also one more step where we adversarially train some of these student models in order to make them like more solid, right? More solid and reduce the transferability. But the whole idea is that if you retrain, if you take a base model, you add some perturbations to the weight of the models, and you retrain them using diversified data sets, you'll hopefully get different models that can do similar inference, but their adversarial transferability is low. Okay. But there is a drawback in this that generating these diverse model pools basically is resource intensive. Okay, so it takes time to generate these model pools, and also there is a bit of transferability because all of them are coming from a common base model, right? So we also saw that there's a bit of transferability that's hard to remove, even if you diversify the training data set and things like this. Okay, so 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 what we wanted to do was, in the context of machine learn, in the context of power systems, somehow strengthen this, right, in order to have like lesser cost of generation, lesser transferability, and things like that, right? And this is where we had the idea of combining the physics-based moving target defense with the machine learning-based defense. So the point is, we are already like doing this topology perturbations, and we have like a rich body of literature trying to design MTD to strengthen the physics-based attack detector. So why not additionally leverage that in order to strengthen the machine learning-based detector? Okay. So what we are doing in this modified design or the combined design is basically at the outset we introduce some physical topology perturbation. Okay. So what this means is the base model itself becomes different. Okay. So let's say FB of omega B was my base machine learning model, and then I changed it because of the topology change. Remember, this machine learning model is also dependent on topology, right? So if you change the topology of system, you also are going to change the base model, okay? And then develop some student models based on this modified base model, okay? Now what happens is that if the attacker has outdated knowledge of system, that means that they know the original base model, okay? And now our student models are now generated from a different base model altogether. So this means that the transferability becomes further, it challenges transferability further, okay? It increases the asymmetry between what the attacker knows and the student models that have been developed, okay? And this is basically a way to get best of both the worlds. What we can show is that if you do this, you can also reduce the number of student models you need to design. It reduces the transferability of the attacks and things like this. Okay. And yeah, I mean, there is additional step of adapting the base model itself, right? Which also needs to be done in real time. But then, thankfully, there are things like meta learning and so on that help in in translating. Okay, so think of meta learning as some sort of generalization of transfer learning. Okay, so you can basically adapt this very fast. In fact, in the context of foundational models, we have things like in-context learning, which is again kind of generalizing this meta learning approaches, right? So a lot of methods can be used to adapt the base model, and the overall system works really well, right? So let me just skip this, but I'll just show you the main results. So here we have different strategies that we use, right? So first, the base one is the MTD strength and DNN, which does not use the physical perturbation. And the best attack detection rate we could get was, about 0.94. And it takes a significant amount of time to generate these models. Of course, all these are based on simulations. Okay, so take it with a little bit of pinch of salt. You may need to test it with some real world data or some more physical test bed. But what we can show is that if you combine the last three strategies are basically combining the physics based with the student model generation. Okay, multiple models plus the physics based model, and we developed several variants of it. Right, I can show that you can get a very high level of accuracy, mainly because of the asymmetry between what the attacker knows and the models that you're actually using to make the inference. And what we can show is that if you only do the physical perturbation, it incurs, increase in OPF cost, the optimal power flow cost, right? So this actually incurs, let's say 1.6% increase in the optimal power flow cost. But if you can combine these two methods, you can actually get best of both the worlds. Okay? You can achieve high detection accuracy, and at the same time, you can also reduce the increase in the OPF cost that you're achieving. So this is like really good because that means that the operator doesn't really have to pay a lot of extra budget in order to get like network security. Okay, so the bottom line is that the combination of these two work really well in mitigating the attack. We have also compared this with several other techniques, things like the ones that are there in machine learning, things like gradient masking, adversarial training, and so on. So the issue with all of these are that these are all static methods, okay? So if attacker is intelligent enough to learn the machine learning inference model, they can also learn some of the static defense techniques, things like adversarial training. So if the attacker can infer the adversarially trained model, That means they are, I mean, they can also bypass the adversarial model as well, right? Whereas a dynamic method like moving target defense, basically, if you do it fast enough, you can invalidate the attacker's knowledge. Okay, so we have compared this against many machine learning based benchmark methods and so on. So that is pretty much concluding my talk. So yeah, I think there are. So what we're trying to do here is basically strengthen attack detection, and moving target defense is this very effective way to do it by changing the nature. So okay, so you don't want to be like a static entity. You don't want to be essentially a sitting duck that the attacker can learn and then craft attack against you, right? So what you want to do is change this asymmetry between attack and defense and dynamically change the system in order to strengthen it. So what we did was we used the concept to strengthen the physics-based detection, and then we used similar models to strengthen the machine learning-based attack detection. Uh, and then there are several areas which you can work on. So there is things of designing a unified moving target defense. So a lot of these moving target defense techniques are like particular to the type of attack that you are considering. Okay, so if you're considering this false data injection attack, then you know that what the attacker needs to know is a measurement matrix, right? So then you're trying to change the measurement matrix to invalidate, right? So in that sense, that attack works for false data injection attack, but maybe it doesn't work for some other type of attack, right? Like let's say DOS attack, maybe it doesn't work. So what you'd want to do is ultimately design some unified moving target defense that can work against different types of attacks. And the second thing you can do is combine cyber and physical attacks. So as I showed on the cyber layer, you can change the line connectivity, network connectivity, or the IP addresses. Right, on the physical side, you can change line reactances and so on. So how can we combine these two, right? So that's again another interesting topic to work on. Other thing is looking at performance guarantees for moving target defense. So the machine learning moving target defense that I showed you, it's hard to theoretically characterize, what is the performance guarantee as opposed to the physics based, where we could actually show that, the orthogonality condition I showed, you can show that basically you can completely eliminate all types of attacks, okay, all types of BDD bypassing attack. Whereas for the machine learning models, it's not easy. So if anyone has ideas on how we can performance guarantees, that would be really good. Then things of looking at the effect of grid transient stability. The OPF is, remember, it's static. I mean, it's steady state, whereas things could happen also on the transients of the power grid. So that is something again that would be interesting to look at. And there hasn't been sufficient real world validation, okay, of this. Okay, so grid operators, as you may all know, are very reluctant to introduce this type of intrusive kind of defense techniques. So it would be really good if there's some real world pilots sort of looking into this and looking at what are the other trade-offs that could happen when you implement it on a real power grid and so on. So I'm gonna stop my talk at this moment, and then I'm happy to take any questions that may be there.
Yeah, thank you so much, Dr. Lakshmi Narayana. And now it's time to take any questions from the audience. Yeah. Yeah, all right. I think I can go first. And while the audience are thinking about the other questions, so I'm very interested in your topic, and especially when you are mentioning the trade-off between the trade-off in deploying the moving target defense mechanisms. So I'm wondering what specific matrices are there that's being used to quantify or to balance the trade-offs.
Yeah, so the way we do it is, maybe I can, yeah, I don't think I have the mathematics here, but like a lot of, yeah, so I've got some other slides. So basically what we do is we cast this as an optimization problem, wherein we are basically saying that minimize the operational cost subject to some security constraint, right? So basically, as I said, the smallest principal angle is this metric that you use to characterize how effective your perturbations are, right? So then you can come up with this kind of optimization problem and say, how can we design this kind of reactance perturbation that gives me a threshold level of attack detection effectiveness and then minimizes the cost, okay? And then by varying this threshold, you can come up with those curves, which is basically what we have done in the plot that I've shown. Basically, we have varied this threshold. Okay, so different varying this gives me different level of effectiveness of the moving target defense, and then it also then gives me the corresponding minimum cost, right? So essentially, you can design perturbations to which are solution to this optimization problem, which then leads to this type of curves, right? So that's how we were able to characterize the trade-off. Yeah, did I answer your
Thank you so much.
question?
Yes, thank you
Yeah,
so much for the detailed explanation.
yeah.
Yeah. Any other questions from the audience? Yeah, Dr. Razuli.
Hello. First, I wanted to thank you for this very interesting topic. Second, for in real world implementation of this method, especially when you were referring to changing in reactances or the topology of the grid, I can think of a couple of things for reactances, like changing the tap changer of transformers. That would be one case, or for the topology of the grid, closing or opening some of the switches. But those are based on the needs of the grid, like if there is voltage changes, the regulators or transformer tap changers come in, or if there is line switching or things along that line, then change of topology come in. Is my understanding correct on those aspects of making changes to the grid physically?
Yeah. I mean, I completely agree. So this comes in the category of trade-offs. So the trade-off that we have characterized is based on the increase in the optimal power flow cost, but there definitely could be other consideration because you may also want to like relieve the congestion in the grid in the one particular manner. So it's always going to be a trade-off, and this trade-off can be characterized in terms of the metrics of that are of interest to the grid operator. And then what you could do is provide this kind of trade-off curves to the grid operator, and then it's up to the grid operator to prioritize, what they would like, how much they want to disrupt the grid versus what level of security they would like to provide. So I completely agree that there could be different ways of implementing this, and changing different things will have like a different set of trade-offs, which of course needs to be studied in detail by grid operator. I haven't really seen any real world implementation of moving target defense yet, at least in the power grid scenario, except people using things like software defined network and things like that for dynamically routing some data on the cyber layer. But I haven't seen many real world implementation of the implementation of the physical layer, which is something that hopefully somebody in the research lab can carry out.
Thank you very much.
Yeah, and also we have some audience left some questions in the chat box. The first question is from Leslie asking, have you also measured the computational energy overhead beyond the OPF implementation cost?
Yeah, so the thing is, so I agree that there is a computational overhead, but what we have seen is that you don't need to make these changes extremely frequently, okay? Because what you would like to do is you would like to change the system faster than the attacker's learning rate, okay? Because basically you're thinking of an attacker that has limited access and they're doing reconnaissance on your grid, okay? So they're trying to learn the grid by themselves. So what you need to do is basically change the system operational settings faster than the attacker's learning rate, okay? And we've also done some background work on understanding how the attacker can learn the system operational settings, right? So things like data-driven learning and so on. And what we realize is that it takes a significant amount of time for the attacker to learn these operational details as well. Okay, so it's not like I need to do this perturbations every 1 minute or something. You have like a big window of time. So that's the reason why I'm saying that there is energy consumption, of course, do all the background computations. But because you don't need to change it like every 1 minute, right? So you only need to change it once in several hours, kind of thing. This overhead should not be very significant, right? And also combining the physics-based plus the machine learning-based, we've also shown that that leads to lower amount of computational time. We haven't computed the computational energy, but it does lower the computational time for sure. It's a good question, but yeah, because there is no real-time requirement, I think it may not be a significant problem. But again, I mean, the proof of the pudding is when somebody actually implements it in a real-world scenario. So yeah, I'd not want to make a conclusive statement on that. But yeah, thanks for the question.
Yeah, I think the second question, you somehow touched on the second question as well. So in a concise way, the second question from Allah asks, can the MTD be viewed as a security-oriented control strategy that sacrifice some operational optimality, and under what conditions, and how frequent would the grid operators expect to activate it?
Yeah. I think I touched upon it already. So you need to do it faster than the attacker's learning rate. And even with the theoretical models, what we've seen is that I don't know if I have any slide on this. Let me quickly check if I have something. Yeah, so what we've done some other work wherein what we are looking at is how can the attacker observe a series of measurements and basically infer this measurement matrix. Okay, so because remember, as an attacker, you have access to the field measurements, you don't have access to the network topology directly. So you would like to access these measurements over a period of time and then infer on the measurement matrix. And then if you apply some signal processing techniques, you can basically learn the column space. But what we have seen is that this kind of analysis, I mean, even in the theoretical models, you can take like several hours. So what we did was looked at the polling rate of the SCADA system, which is every 4 to 6 seconds, and then we looked at how many measurements are needed, and then we came up with a approximate time. And what we saw is that it needs attackers several hours to learn the measurement matrix, even in a theoretical model. Okay, so in a real world system, of course, this can be like even more. So that's the reason why we think that it doesn't need to be real time in the order of minutes. It can be several hours. And there's also other work where people have done something called as event triggered moving target defense. So you have like a base detector, like a machine learning based detector, right? So you wait for it to give some alarms. You don't keep changing it every 1 hour or 5 hours or whatever, right? You wait for the machine learning based detector to give you some alarms, and then once you get the alarm, then you use moving target defense to basically confirm those alarms. Okay, so just using machine learning, I mean, machine learning can throw up a lot of false positives, right? So what they've done there is basically use MTD as a way to reduce the false positive rate. So you wait for the machine learning to give you a trigger, and once you get the trigger, you then verify it using your moving target defense and things like that. So that's what they call as event triggered moving target defense, which can further reduce the frequency at which you make these changes. So yeah, I hope
Oh,
that answers the question.
Okay,
thank
so
you.
can I
Oh,
ask a question about the slide 31 and also the one you just showed? So basically, the perturbation is essentially just changing the value of that NT, right? So yeah, but
Yeah, I mean, you change the line reactance, which then changes the measurement matrix, the elements of the measurement matrix. Yeah.
okay, so by changing the value of NT, then you introduce different kind of the perturbation.
Sorry, what is NT? Do you mean by this one?
No, I mean, so slides, the one you just showed. Let me see.
Here. This
Yeah,
one.
yeah. So by changing NT, then you actually just try to change its angle, from your previous operating plan.
Sorry, so NT here is just the noise. NT here is just measuring the noise. I mean, if you worked around this topic, basically the H matrix depends on the line reactance. and the topology. Okay. And it's a matrix you can derive. If you know the line reactance, if you know the topology, you can derive this matrix H. So if I change the line reactance of the network, that basically changes my H matrix.
Oh,
And by changing different line reactances, you can get different orientations of the pre-perturbation and the post-perturbation matrix.
so by changing that H matrix, basically you change your operational status. Is that?
It changes the operational status, but then it also invalidates the knowledge the attacker requires to craft the attack. And that's why I said there is a trade-off, okay? Because you're changing the operational state on the one hand, but on the other hand, you're also invalidating attacker's knowledge. So this gives you some security. So there is a cost to pay, which is basically changing the state of the system, right? If you change line reactance, that changes your power flows and things like that.
I see. Okay, thank you.
Yeah, thank you again, Dr. Lakshminarayana. And if there's no more questions, I think that's the end of the webinar.
Yeah, thanks again for inviting me. And yeah, I mean, I'm happy to be, if anybody wants to follow up slides or any papers, I'm happy to share them.
Yeah, you can find the Dr. Lakshminarayana's email address on the flyers. Yeah. All right. Thank you all.
Thank you. See you.
Bye-bye.